Alright, gents, Chapter 5, Spanning Tree Protocol Concepts. This is 45 slides. So, the material for this chapter is to look at how switching fabric controls the links, redundant links within the network, and we'll go over some of the protocol history and also explain how it operates. So the purpose of spanning tree can be displayed like this. You got the switches, you turn them on, plug a cable in. So you go from top, middle to bottom, and to be fully redundant, we'll also go from bottom to top. And their lights come on to green, orange, then green. So the orange is while they're negotiating and setting themselves up. And then the third one is negotiating and they are on. And then one of them turns off. This one in the middle. So basically what that means is it's not forwarding traffic through that port. That's what spanning tree does. It breaks the loop. Now we'll explain why it does it and how it does it. So there's a bunch of text there that basically says, you know, we need a way to stop loops at layer 2 because there is no mechanism within the layer 2 protocol, so i.e. Ethernet, for us to break any broadcast storms or anything like that that happens. Now, you're going, but there's time to live. Yeah, but that's layer 3. Alright, so we have a maximum hop count or time to live features within the IP packet, but that's at layer 3. This is layer 2. So if something went wrong and traffic was just continuously traveling in the loop, it would be there forever. So we need the alternative pathing which generates the loops, but what we don't need is all the links running for all the traffic all the time. So we need to generate a loop-free topology that will generate a single path between any two switches within the topology. So what's a broadcast storm type event? So one of the most common causes of a broadcast storm would be the corruption of the MAC address tables in the switches. So we've got A sending something to B. B, something happens, it fails at the time of the ARP request. So the ARP request, as you know, is a broadcast. It sends it out to every device. So the switches record the MAC address of A as they come in, forwards it out where it leaves B to be. Those go straight past B because B is no longer in play, and re-enter the switches on the other end because there's a loop. And the tables are now updated with port 2 as the source of the MAC address of device A, and it rinses and repeats and continues to do that. So spanning tree is designed to knock out that loop, and this will allow us to have a redundant network but prevent frames from circling around in our topology forever when something goes wrong. So spanning tree compensates for a failure within the switching fabric by opening the previously closed port. Now, it's not closed as in shut down, it's closed from forwarding traffic. So they call this as a blocked port. So it can't forward. So what this does is it provides us with the ability to create redundant networks by eliminating a single point of failure within the tree, and we control the port so that a layer 2 loop doesn't exist. So that eliminates the potential for our traffic to continue to affinity and beyond. Okay, and the bottom one is talking about the layer 3 time to live and the fact that we have a maximum number of times that we can go through layer 3 devices before that time to live counter expires and the device is terminates that packet from being forwarded on, and there's no mechanism for that in Ethernet. So what happens is, without spanning tree, loops form and a broadcast or a multicast can circle the traffic loop forever, and this can bring your switch network to its knees very quickly, because every time a broadcast is sent, and as you know, lots of our protocols and excuse me, I'm quite froggy this morning, can generate broadcasts very quickly, because every time it needs a match up between a layer 2 address and a layer 3 address that it doesn't have in its own MAC table, it sends an ARP request out, which is a broadcast. So the network quickly becomes packed full of all these broadcasts, and your legitimate data can no longer get through, which kills the equipment, because the CPUs of the switches and that can't keep up with all the recalculations. So this is a broadcast storm where everything's going around. All these things are being sent, and there's many reasons why they could occur, but they cannot be stopped unless you turn off your switching fabric. Okay, you need to break that loop by turning off a switch. This is where spanning tree comes into play. It discovers these loops as the ports turn on. They send a little discovery out, and the switches learn if there's a loop or not. Well, sorry, spanning tree learns if there's a loop or not the switches per se. So the algorithm is invented by Per-VLAN, and back in 1985, such a long time ago. And her algorithm creates a loop-free topology, and it does this by selecting a single root bridge, and all other switches within the fabric now determine a least cost path to that bridge. So you basically have spanning tree going, this is the master switch, all paths shall come to me. And this prevents loops by calculating that, oh, I've got multiple ways of getting to the same point. I'll block one of the ports so that I don't have a loop. And if something goes wrong, all what I've got to do is unblock that port, and I've got that alternative path back, and I can continue to send traffic. So it's a way of creating a redundant network that is safe and secure at layer 2. So by selecting the root bridge, this is the reference point for the entire spanning tree method within the switches. It then blocks a redundant path, so it creates only one logical path within the spanning tree, thus eliminating any loops. So a port that is blocked can still receive information, it just can't send information. So it's still monitoring the network and hearing everything that's going on, it's just not forwarding data. Okay, so this blocking of the port generates your loop-free topology with a single path up to the root bridge. When a link goes down, it's got to do a quick recalculation to re-bring up those block ports. Okay, so it recalculates the paths and unblocks the ports that it needs to unblock to provide a path back up to the root bridge. Now, these recalculations occur whenever there's a link down, a new switch is added in, or a new cable providing inter-switch connectivity. So the 4-step process, and yeah, you need to know this. Unfortunately, it's going to It's a must know because spanning tree is a key protocol for layer 2, and we need to understand how it works. So first step, elect a root bridge. Second step, elect root ports. Third step, elect designated ports. And fourth step, elect alternate ports. These are the ones that we block. So how does it do this process? Well, it sends out a little packet. Well, it's not a packet, it's a frame. It sends out these bridge protocol data units, which are a little control frame that spanning tree uses. And within that, it has information that it uses to elect the bridges, the ports. Okay, so what's in this information? Well, strangely enough, it has the bridge ID, which is an identifier of where that particular bridge protocol data unit originated from, and it'll have a priority value which is equivalent to the MAC address, okay, because they all start up with the same priority value. So the bridge ID is this priority value plus the MAC address, and this is what determines a lot of information and the existence of the loops. So bridge priority is a decimal value and the range increments between 0 and 61,440 in increments of 4,096. Alright, so the default value is 32,768, and again, that's one of those key values that you need to know. The lower the priority, the higher the precedence that switch has. Okay, so for a root bridge to occur, it has to have the lowest value in the bridge ID. Now, Cisco uses an extended system ID, which it adds to the default bridge priorities system, and this is the VLAN that it's running on. It's just a little quirk that they do. So for every VLAN that's running, you can create a separate priority. We'll get into that later. Alright, so not only do we have the priority that the bridge generates, as in the default 32,768, it then adds the VLAN ID number to it, and then adds the MAC address. And this is what it uses to determine who has the priority for becoming bridge. Remember, the lowest value equals the root. So if we have a look here, we have our 3 switches, and if they are all on default values, the lowest bridge ID, because all the priorities would be that same value, which is 32,768 plus the VLAN. Our default VLAN is 1, so in this example our priority ID is 32,769. So if that was the only deciding factor, the lowest bridge ID would be on switch 2 because it has the lowest MAC address. But switch 1 has been adjusted to have a priority of 24,577, which means it now has the lowest ID and it will become the bridge. Now, you want to designate the bridge. You want to control this because the device with the lowest MAC address generally is your oldest device in your network. So you want to be able to manually adjust this so you control where that root bridge is. And when we connect it to the routers for inter-VLAN routing, we tend to want that as our root bridge so that all the traffic flows up towards our gateways attached to our router. So we want to control this election process. Okay, so all this text is just going through what I just said on the previous slide. I don't really need to read out all that text word for word, do I? I know, I really don't want to. Now, when the root bridge is elected, it needs to now determine where all those destinations are and the costs involved. So what it does is it sends out its little data units, and as they start arriving into the switch, it adds the cost of that port onto the cost of the path towards the root bridge. So the default costs are laid out in the standard. So these are defined by IEEE, and they're a couple of different standards. So we've got standard spanning tree protocol, and we have rapid spanning tree protocol, and we've got some others that don't come up until we're doing an advanced routing switching course. And so we have column A, which is our speeds, and the first one is the standard spanning tree. Now, these values were changed in 1998 because prior to that, the maximum switching speed anybody thought possible was 1 gigabit per second. Anything from there onwards was a cost of 1. So it really, remember spanning tree came out of the days when the maximum speed was 10 megabits. So 100 megabits was really stretching things, and then a gigabit they just thought was impossible, and they certainly didn't think anything above that was possible. So these values were changed in 98 to reflect this new high-speed switching that we have. So 2, 4, 19 and 100. Why they did 19, I still can't fathom. Why they didn't just make it 20 so that people could calculate it nice, simple, easily. Yeah, no, can't do that. Rapid spanning tree has its different cost factor. and it's, 2,000, 20,000, 200,000, and 2 million. So the slower the speed, the really, really more expensive that path is. So, electing the root ports. The PDUs go out, and as they come around, okay, from switch 1, it sends it out F02, and arrives here on switch 3, and it adds the cost of trunk 3 to that port, saying the root bridge is the cost. So if we're running 100 meg links, the cost is 19. Coming down this way, same thing. PDU comes down into this switch port, cost back up to here is 19. I then forward that PDU up to switch 3, because remember, it's still in the process of learning. It hasn't shut any ports down yet. So it gets to this port F2 on switch 3, and it has another 19, which is 38. And then it arrives back at the root bridge. Now this has occurred in both directions. So it now knows that it has a loop, and it has 2 paths to get to the root bridge for switch 2 and switch 3. So switch 2 goes, my lowest cost is 19, so out of F1, because my alternative is F2 with 38. So I'm going to designate F1 as my root bridge, and same with switch 3, the lowest cost. Now, every other port is now going to rotate up to designated. So every switch has to have at least one designated port. This is our path to the root. So we now have root ports, that is the closest port to our root bridge, and then designated port, which has a path to the root bridge. So all the ports on the root bridge become designated. The best path on the other switches become root ports. And then we then go, well, we've got designated ports, but we've got 2 designated ports on the same link. We can't have that. So one of those designated ports becomes an alternate port or a block port. Now it's going to take you a little while, because not all the rules for finding these out have been explained yet. So designated ports can forward traffic. Root ports can forward traffic. Alternative ports cannot forward traffic, so they're blocking. What we haven't explained is how does it decide what's what. So when we have multiple ports of equal value going back to the root, the switch needs to use the following criteria to determine the lowest cost port. So we've got the lowest sender bridge ID, then if that all is the same, lowest sender port priority, and then the lowest sender port ID. So when we're looking at the loop, we have a look at where we are in the network. In this example, they changed from 3 switches to 4 just to make life different from all the other examples. Okay, so we look around, look at the bridge IDs, and we've got a clear winner at the 24,000. So this is our root bridge. PDUs go out, determine, okay, this is my root bridge because it's the shortest cost to the bridge. This is my root port because it's the closest to the bridge. And then down here, it's going, I've got an equal cost going that way and going that way. So I now need to work out which is the lowest cost. So the path going this way, all right, so the sender's bridge ID, so switch 3 has 555 and switch 4 has the same priority but 111s. So switch 4 has the lowest bridge ID, so forwarding traffic to the lowest ID becomes the root. Alright, so the lowest ID that switch 2 receives, because it's got the alternative paths, is decided on. This is lower, so it becomes the root. Designated ports. Well, all the root bridge are designated ports. Every other switch turns their other ports to designated ports. Then we come back to our little one with equal costs back to the root. And again, it says, I've got a problem because I've got to break that loop. This is my root bridge. Therefore, I should normally turn this to a designated, but as I've got a loop, I'll change this to an alternative port, thus breaking the loop. So that same simple calculation determines the function of each port, all based to the cost of the root bridge, using these simple criteria. lowest sender bridge ID, lowest sender port priority, lowest sender port ID. So what happens when it's dual link between two devices? Well, the sender bridge ID is going to be the same. Port priority is the same. So what's the deciding factor of which one's going to be on and off? Well, this is the root bridge. So with switch 4 has to determine which port is what. So both ports that it comes in on is receiving the same bridge ID. It's receiving the same priority. So what's the deciding factor? Goes back to the last one, the actual port ID. 5 is lower than 6. So which one do you think becomes the root? Now, did anybody pick up my false trail? It's not about the port that it comes in on. It's about the port that is sent. So let's go back those few slides. Sender, sender, sender. Lowest bridge ID, lowest port priority, lowest port ID from the sender. So the PDU that arrives, this is very important. So when we're looking at from here, the deciding factor, because the receiving PDU comes from the same bridge, they both have the same port priority, so the deciding factor is the lowest port ID, which is 1. So this becomes the root, and then because this is the alternative port, because it can't be designated, because the other end is designated. So it becomes the alternative port. So how does it keep track of all these links and the changes within the switch fabric? Well, it sends out these little data units every 2 seconds. And you go, geez, that's a lot of traffic. Yes, it is. But you've got high speed, so it's not a large frame. It's very small. And the other thing it looks at is the forward delay timer, which is the delay in changing states. So going from listening, learning, and then transmission is 15 seconds in each state. So we can modify that by changing the timers on those states. But the maximum age of the timer So the time it waits before it says there's been a change in the topology is 20 seconds. Again, this can be modified between 6 and 40 seconds. These timers can be changed on the root bridge. The root bridge defines the timers within the domain. And if you think about it, they're all in increments. So let's have a look at the timers. So if nothing's received, the maximum age is reached at default at 20 seconds. It then brings up a listening stage, which means it's trying to determine what's going on. 15 seconds. Okay, let's learn and populate the MAC address table with frames as they come in. Another 15 seconds. Then I'll start forwarding. In this listening state is where it's receiving those protocol data units and doing the election of route and designated ports and all of that lovely stuff. Remember, it should be receiving those every 2 seconds. So it now knows where it lives within the state of the spanning tree and can start forwarding. So the port states blocking, it only receives the protocol data units, doesn't update the MAC address, and it doesn't update the forwarding of information. Listening receives and sends the PDUs, doesn't update the tables, doesn't forward traffic other than the PDUs. Learning, it's still receiving and sending the PDUs, but it's starting to update the MAC address table ready for forwarding. It's not going to forward any data, but it's getting itself ready. Forwarding means we're sending and receiving everything, and disabled port means it's shut, it's turned off. It's not sending or receiving anything, it's not updating anything because it's off. So that should give you an idea of the states. So if you're just coming through, first state goes blocking, then it goes into listening, learning, forwarding, 15 seconds each. So you've got a good 30 seconds from you plugging in the cable before it decides whether it's going to forward or not. Now, if that cable is connected to a PC that's turned on, looking for a DHCP server, it's not going to get a response for at least 30 seconds, which means the DHCP cycle on your device has expired. So it'll go to that, oh, I can't find a DHCP server, I'll just automatically assign an internal IP address to my device. Just be aware of that one. There is a spanning tree that operates with multiple VLANs, but the default one on Cisco devices is a Per-VLAN spanning tree. So for each VLAN, it calculates its own spanning tree instance. So you could have multiple root bridges spread out across the fabric for your different VLANs. So this is the method that we use to manually control our traffic within layer 2. And you go, what? Well, think about it. If all the VLANs were running the same spanning tree, it means all the ports would be in the same state. So all the VLANs would have the same link closed at the same time. By creating a different spanning tree instance for each VLAN we are running, we can force different VLANs to use the redundant links at different times. So we can manually load balance across our uplinks to make use of our redundant paths so that not all traffic is going down the same path at the same time. So if one of our links fails, it only upsets a portion of our network traffic while it repasses to the alternative ports. And this is a good way of reducing the overall traffic on our uplinks towards the root bridge. So back to our little diagram. What is the lowest MAC address? C00 is lower than that one and that one. So we have our root bridge. So connect these two together. Our third one comes up, and what's going to happen? PDUs are going to be sent. So this one comes up because it was physically connected first, no loop. Second link comes up to listening, receiving PDUs down, still no loop, all good, turn them on. Third link comes up, goes through its listening, learning phase. So it's going on the bridge ID. I've got a bridge that way. Now I'm getting bridge coming in this way as well. So we now have a loop. So where's our root bridge? Here. Why? Because by default, every device has the same priority. And the MAC address is the deciding factor. So the top device becomes our root bridge. So our middle device now has two paths to the root bridge. and so does our bottom device. So on the middle port switch, what becomes the root bridge? This becomes the root bridge, this becomes the root port, because it's the lowest cost to, and I just clicked the button, let's go back one. So it's the lowest cost to the root bridge. What about the bottom switch? Well, the lowest cost to the root bridge is this cable here, because it's cost of 19, PDU arriving there is 38, PDU arriving there is 38. Alright, so we've got two possible designated ports. So what is the cost of the PDU as it arrives here? Well, the sender ID is 00OC01, so the first half is the same. They're the same vendor. Congratulations. FF against FE. What's the lowest cost? FE. FE is lower than FF, so I'm going to shut down the one that costs the most, which according to the bridge ID that is sent between the two ends of this cable, this is the most expensive source. So I'm going to close that port, and now I have a loop-free environment and all the ports are designated, root, alternative, root, designated. No. Well, they were drawn in, but not live. Okay. They're drawn in the PowerPoint, and there's animation attached to the slide. So basically, the raw content of that slide is very messy. So basically the animation turns off different elements within the slide to provide the picture. Alright, so this concept of the election of spanning tree root bridge, the root ports, and designated and alternative ports, it's quite a big one to grasp. Okay, and it's very important because we need to be able to understand this election process so that we can control it. We want to define what port switch gets elected as the root bridge. We want to select or control the election process all the way through. So our different versions of spanning tree, alright, the main one was spanning tree protocol, then we have rapid spanning tree protocol, multiple spanning tree protocol, and this, standard spanning tree basically says, yeah, nobody really wants or should use spanning tree anymore. We should really use rapid spanning tree from 2004. And there's not a great deal of differences between these two protocols. It basically is what shall we say? The timers are by default different values. So rapid spanning tree becomes active into the forwarding state much faster than the standard spanning tree did. Now, Cisco implements their own versions of these, which is Per-VLAN spanning tree, and it basically implements the standard the same, except that it runs the spanning tree instance for each VLAN. So basically they're following the standard pretty much the same, but the difference is they're going to say, I'm going to modify this a little bit, so I've got an instance per VLAN. So the versions, spanning tree as per the update D version was 1998. Then Per-VLAN spanning tree was instigated by Cisco. Then the spanning tree protocol was updated in 2004. Rapid spanning tree was evolution that provided faster convergence. In other words, the rules about listening and learning and the default 15 seconds were changed. Cisco went, well, if this is now going to be like the new standard, we better update our Per-VLAN spanning tree to cater for this. Because guess what? We still want to have control of each VLAN and the spanning tree so we can load balance between the switches. And there is, under rapid spanning tree, some new terminology that you need to get your head around. There's port fast, PDU guards, PDU filters, root guard, loop guard, and basically all what these are ways of locking in, manually locking in our election process, so how we rig the election. Multiple spanning tree has been kicking around forever, and I just noticed this table falls off the bottom of the slide, which is not so good. Let's why are you not starting up? No, that went worse. That's not what I wanted. Darn you! Alright, I'm going to have to change this offline. Okay, so multiple spanning tree is where we can selectively add or bundle the instances of VLANs together. So we basically bundle VLANs into the instance, and then we can control the groupings of VLANs with the multiple spanning tree. Basically, so you've got a standard switch layout of 3 switches. You have a loop because it's a redundant path back to the root bridge with multiple. Say you've got 20 VLANs running on it. You don't want to be constantly calculating and sending PDUs out for 20 VLANs. So what we would do is instigate multiple spanning tree and go, we're going to group all the odd number VLANs in instance 1 and all the even VLANs in instance 2. Boom. And what we're going to do is shut down the different designated ports on. Okay, so if we went back to this example here, alright, what we can do is go, alright, for multiple spanning tree instance 1, this is going to be the alternative port and be blocked, because that's where our loop is. On instance 2, this is going to be our designated port and this one's going to be blocked. That means this link is being utilized by half the traffic in the switching fabric. So we've got instance 1 and instance 2, both with a loop-free topology to the root bridge, but with different designated and alternative ports, so that any duplicate links will be shared and in use between the different instances. It just means we can not overload any given link with all the traffic all the time. It's part of our redundancy, so that we are utilizing the resources to its best capacity and we don't have a single point of failure for the entire switching network. So rapid spanning tree, which is 1W, supersedes 1D. But basically it goes to the forwarding quickly, as in it basically skips the listening and learning and just goes in the forwarding mode, which can be a bit dangerous. We'll worry about that when we do specific ones on rapid spanning tree. So it basically jumps to the forwarding point, which is fantastic when you've got host machines connected to these ports, because you're not going to get, go through that 30-second delay and having to reset all of your devices to get reconnected to DHCP. But it has some issues, because if everything's in forwarding, then you're going to have loops and that could cause problems. So we've got to have a way of controlling that. But that's for another time. Let's move on to the roles. So we have standard on the left, rapid on the right. So in the initial startup, where you have disabled blocking and listening. Boom. No, I'm not going to do that. I'm just going to discard everything and just go to learning and then forwarding. You go, well, that would save 15 seconds. So it's going to be up faster by default timings if you compare to spanning tree. Now, if we look at the port status, root ports, same. Designated ports, same. Block port or non-designated port, oh, hang on, we've got a difference here. We have backup ports and alternative ports in rapid spanning tree. And I'll give you a heads up, backup port can come straight up. It doesn't have to go through the learning, recalculating. They can be instantly brought back online if a link fails. Alternative ports still need a recalculation. So the designation of those things, backup ports, the hubs, now you're never going to find that in networks now. Who will have hubs? No one. Okay, so the way rapid spanning tree treats our designated and alternate ports in this quick changing environment is it can bring up these ports on back into a forwarding position much faster than it can under normal spanning tree. PDU guards. So forwarding delay timers under normal condition, 15 seconds for each state, 30 seconds to come up. So DHCP dies without a response. So if we designate a port as port fast, we go from blocking to forwarding immediately, saving 30 seconds. This should only be enabled on ports connecting to access devices. So a port fast enabled switch port should never receive bridging protocol data units because it should only be connected to a client. If it receives a data unit, it means it's no longer connected to a host and it will go into error disabled state to protect the spanning tree from potential loops. You need to go in and manually reset the port to bring the port back up online. So our need for speed and greater availability has changed the way organizations want to have their network respond, and this is why we need to adapt the protocols that work to keep our switching fabric loop free. So this is why spanning tree has evolved to rapid and multi-spanning tree additions, so that the network can adapt to changes, as in failure or changes in topology, quickly and predictably. And it's basically there to support our layer 3 functions. Some organizations cannot have the problems that occur within switching fabrics when spanning tree fails. And it can fail, and it fails spectacularly in large networks. So these large organizations are moving to a layer 3 switching fabric, thus eliminating the need for spanning tree to work. So basically you're having multi-layer switches acting as access layers, which is pretty damn expensive. But it eliminates the need for spanning trees. So there's some packet tracer activities and lab activities that you should be doing along with your studies. There's a lot of text involved in reading this one. So basically what we did was have a look at the fact that layer 2 is prone to instability because of the way the links can be formed and become unstable with excessive traffic. So we want to have a mechanism to help prevent loops from occurring, and we want to have it some method of having it automated so that we don't have to manually configure every port as forwarding, blocking. So we have a spanning tree protocol that comes in and goes through a 4-step process of electing a root bridge, electing root ports, designated ports, and then alternative ports to control loops within our network. We looked at how this election process takes place and the information that is basically contained within the bridging protocol data units used to form these elections, and how we can manipulate the election process to have the devices elected in the order that we want them to be elected, and how we can also elect the root ports so that traffic will flow in a way that we wish it to flow across our VLANs. We looked at the timers. So the PDUs use hello timer, forwarding delay timers, and max age timers to control the states of the ports. these three states are listening, learning, forwarding, and the other non-active states are blocking and disabled. So we looked at the fact that to transition through listening and learning by default is 15 seconds each. So we can then look at how long it will take to come up, and we looked at the evolution from standard spanning tree protocol across the rapid, and we had a look at Cisco's implementation of those protocols on their devices. They did a little modification by adding the VLAN ID so that they control the spanning tree for each VLAN that they have implemented. We looked at how port-fast is used to basically transition directly to forwarding, avoiding our 30 seconds of delay, and where it should be used and where it shouldn't be used, the safeguard for protecting spanning tree that is in place for port-fast. So port-fast is only to be activated on ports directly connected to host machines, and we would have an instant shutting of that port if it ever received a PDU. So the idea is we use the version of spanning tree applicable to our environment, depending on our organization needs. And if the organization is big enough, it may decide to bring layer 3 connectivity into the switching fabric as close to our access points as possible to eliminate the need for spanning tree, so that we do not have the issues with our redundancy and transitions between forwarding and blocking of ports, because layer 3 responds to these issues much faster than layer 2. So that's the end of me rambling on about the theory. All what I can say is to get there and to play around with it in Packet Tracer, see how it does the election process, see how you can change that election process in the labs, because by doing those labs with spanning tree, you get to understand how spanning tree works, and with that becomes the joy of having a fully redundant and relatively stable network.